Welcome and hello. This is a video exercise in WRIMS, and what we're going to be doing in this exercise is solving a nonlinear problem using linear programming. So what we're going to be doing here is using linear programming for perhaps not its intended purpose, but using successive approximations, we will be able to solve a nonlinear problem with multiple iterations as we slowly converge upon the correct answer. All right, so let's go ahead and get started. I'm going to put up a model schematic to show you the specific problem statement I have in mind, and then we'll talk about that as an introduction. Then we'll get into the model, build it, look at the code, and then run it multiple times to effectively solve the problem I have on the screen here. This is a network flow problem. It's a very simple parallel pipe type of problem where we have an inflow of 10 CFS coming in from the left. It enters node 1 and then it flows through pipes A, B, and C to node 2 and then out of the system through this pipe D, or we may call them pipes or channels. I'll call them pipes. Okay, what we know from hydraulics is, of course, the head loss through each of these pipes is the same to sort of balance out. But what we don't know is what is the actual flow rate through each of these pipes. So this is your standard introductory to hydraulics type of problem, but we're going to be solving it using WRIMS. Over to the right, we have a properties table. So each of the three pipes here have their own row in the table. And then the F refers to the friction factor. L is the length of the pipe. And then D here is the diameter of the pipe. The next slide shows the head loss equation. So we have the friction factor times L over D times V squared over 2G. If we expand the velocity term to be Q over A, and this is what we have here, 8FL flow rate squared, and then the A, represented as diameter squared over 4, and then square that, we would have the denominator here, which is G pi squared, and the diameter raised to the 5th power. Now, below that, we have this term written out 3 times with a subscript A, B, and C, representing the pipes A, B, and C. So we know that this bottom equation is true, but there's also a lot of repetition. For instance, we can cancel out the 8 as well as the G as well as the pi squared terms. Those are all constant and present in all 3 of our terms. So we do that, and then the next line down here is ready for plug and chug. We have FLAQ squared over D to the 5th for A, B, and C are our pipes. So if we use the numbers in the table right here and plug them in, okay, there we go. So I've plugged them in and then I've solved for the coefficients. So for QA squared, the flow rate through pipe A squared, we have a coefficient of 8.0566. For pipe B, it's 2.4, and then for pipe C, it's going to be 1.7683. Okay, that's what I'm calling equation 1. We also have an equation 2, which is a little simpler to understand. It's just the flow rate through pipes A, B, and C must equal our 10 CFS. So what we're looking at here is 2 equations and 3 unknowns. We don't know what the values are for Q, A, B, or C. So what we're going to be doing in this problem is to start with an initial guess. Our first iteration will just be a guess, and we know the flow rates add up to 10. We'll devise this sort of network in our WRIMS program. We'll build the model, we'll run it, and then we'll see what values WRIMS gives us for modeled flow rates. So here's the last slide I have prepared here. We have our equation 1, our equation 2, and then our first iteration, there we go, is going to be 1, 4, and 5. Now I chose 1, 4, and 5 just simply because I'm an engineer and I can just tell that if I go back to this equation here, we know that the diameter term here in the denominator is raised to the 5th power, which is a lot larger order than any other term in the head loss equation. So quite clearly, the diameter is going to be the most influential with regard to head loss. Even though pipe C has a higher friction factor, that's just linear, and it even has a longer length, but that's again just linear. So I've ordered the flow rates in terms of the diameter here. So the smaller the diameter, the smaller the flow rate. Okay, again, that's just a first iteration guess. We could be off, but I'm pretty sure that will be the correct ordering. But the most flow through pipe C, the least through pipe A. Okay, let's stop talking and start building the model. I'm going to open up my WRIMS application and then right-click to create a new project. In the Project Explorer, just right-click New Project, and then with General Project selected, click on Next. Give your project a name, just type it in or paste it in, and then uncheck this Use Default Location. and I'm going to bring up my project directory here. This is the path to the project directory I'm going to use for this exercise. So there it is, and then click Finish. Okay, so over here in my Project Explorer window, I have a new project created. I'm calling this Network Flows. I'm going to create a configuration now, so just right-click on that project, come down here to Run As, and Run Configuration. I'm going to click on Russell/RIMS to application, and then click on this new button to create a new configuration. All right, so the name I'm going to give it is E9 Network Flows. I'm going to come down here to the main Russell file. I haven't created this file yet, but I'm going to put it in a run directory and just call it main, WRESL. All right, down below that, I need a file for my decision variables. I'm going to put that in a DSS directory, dv.dss. And then after that, I'm going to also create two more DSS files, which I think are required just for the program to run, but we won't be actually using state variables or a init.dss file. Further down, I'm going to just type in project for my part A, state, and init. And then for the time step, 1 month is fine. I only need one time step to solve the problem, but I'm just going to use 1 year. So I'll select just one water year here, 1922. That looks good. I'm going to have 12 entries because it's a 1 month time step, but it's all right. Okay, the next tab over is configuration. So click that and then click on the checkbox to use the Russell Plus engine or the interpreter. And then common is the far right tab. So click that. The last thing we need to do is click on the shared file radio button and then click the browse and then select the name of the project that you named earlier. And OK, and apply and close. Okay, so we have our launch file created. That's what we just did by creating the configuration. That's what I want to do is set up my directory structure. So here is the project directory, at least how I want it to look. This is the main project folder. And then here are the two files we already have created. Everything else I still need to create. So I need to create a DSS folder, a run folder, a systems folder, and then a few other files. So let's get started on that, and then we'll start building the network. Here's the project directory once again. So I'm going to go right-click, New, and then create a DSS folder. Oops, I always do that. DSS, there we go. And then while I'm here, I'll create my Run folder as well. Run. In the DSS folder, I need to create those 3 DSS files. So right-click, New, and then I'm going to select Text Document. I'll just go db.dss. There we go. This should be the same relative path that we typed into our configuration. So this is sv.dss. And then, yeah, if you want to just copy this blank file, hold down Control in Windows, and then left-click, drag, right-click, and rename. This is our init.dss. Okay, let's go up a level now, and then into the run directory, I need to create a main.russell file. There's that. And then also a system directory. This is just the structure that I've set up, but you can set up your system however you want. And then I need 3 files here, inflows, channels, and constraints. No objective function. We're not doing that. And constraints. Okay, so those 3 files are ready to go. Let's go ahead and open up the files and start making edits. So here is the inflows file. I'm going to go ahead and open up the others. So that's channels and constraints. And then we also need to go up a level and get our main Russell file. So the inflow file is right here. This is the simplest state variable you can assign. It's basically the name of the variable and then the value of 10. So that represents the flow rate through the inflow to the system, which is this right here, 10 CFS through I1 into node 1. Back to our files, channels. This is our 4 dvar decision variables A, B, C, and D. So after we run the simulation, we're going to come to look at these 4 paths and take a look at their values. We already know that D is going to be 10 if I set up the constraints correctly. And then here are the constraints. So there we go. If we scroll up to the top, the first couple constraints here are continuity. At node 1, we know that the inflow of I1 equals the sum of the outflows, which is the flow leaving node 1, which is the flow rate through pipes A and B and C. Same deal with node 2. Entering is A, B, and C, and then leaving here is the flow through pipe D. Further down, this is a little bit more involved. What I'm doing is I've got 3 soft constraints, goal AB, goal AC, and goal BC. Now, this is sort of taking the place of the objective function. What we're trying to do is eliminate or reduce penalty. and penalty has occurred if the left-hand side is not equal to the right-hand side. Now, this may look a little bit interesting, so I'll explain it. This right here, 8.0566 and 2.4, that is the same as 8.0566 and 2.4. Now, what I would like to do, but I can't because this is LP, is I would like to say a squared, and I'd like to say b squared, and solve it in one single iteration, but that's not allowed. So what I'm doing is I'm populating the variable b here as a linear term. And then for this b, I'm going to insert my first guess. Same thing with the line above it. Left-hand side is going to be my guess for the flow through pipe A times the calculated flow through pipe A. And I'm doing the same thing down here for AC and BC. See, what I'm representing for C now is 1.7683 times the initial guess times the linear term of C, not the quadratic. So what's going to happen here is we're going to get a value for A and for B and for C, which is going to satisfy this solve constraint. And whatever that number is, say it's 2 or it's 3, then we're going to know that this left-hand side, all right here, is going to equal this right-hand side with whatever value B is. And then it'll be up to us to determine what should we use for our guess in the second iteration. So let's just go ahead and get started. You'll see how this works. We're going to go through a number of iterations here and keep track of all the numbers, both the assumed flow rate at the beginning of the iteration and then the calculated flow rate at the end of the iteration after the computations are ran. Okay, so we have one more file. That is this one here. It's our main Russell file. Again, we're just going to be calling the inflows, the channels, and the constraints. So let's go ahead and save that and see what it looks like. I'm going to click on the WRIMS. And then actually, let me refresh this just to make sure we have our directories. Okay, it looks good. On the launch file, I'm going to go right click, run as, and then run it. Okay, so that looks like it ran. I need to bring up DSS view here so I can open up that dv.dss file. I'm going to click on open. I'm going to navigate to the project, DSS, and dv.dss. Okay, cool. So we have data here. We have our 4 paths at the top we're interested in. A, B, C, and D. If I click on the table, we can see what those values are. All right, interesting. So we have 3.636, it's not that high, 3.051, and 3.313. These are the flow rates that were calculated for variables A, B, and C on our first iteration based on our initial guesses of 1, 4, and 5 for A, B, and C. So to keep track of what we're doing here, I have created a results table. Let me go ahead and move this there. Okay, that's good enough. We have iteration 1 and the assumed values of 1, 4, and 5. Now what I'm going to do down here is type out the calculated flow rates based on the model, 3.636, then 3.051, and 3.313. Okay, so now it's telling me the flow rate in pipe A is the largest. I know that's not true. What I'm going to do here for my next iteration is split the difference between our assumed and calculated flow rate. Now, I could use an arithmetic mean, I could use a geometric mean, I could do something else, some other search term, but I don't want to just plug in these numbers right here. I feel like that could cause instability. We could start searching in the wrong direction. The actual best next guess is a whole science in itself, but let's be simple about it and just say round, average, and then these 2 values right here, and then 3 decimal places. So I'm going to copy that over. So what I'm going to use for my initial guesses on the second iteration for flow rates in pipes A, B, and C will be 2.318, 3.526, and 4.157. So I'm going to minimize that, close that, minimize that. Back to our files. I need to update the constraints file now. So let me just paste in what I have. So we have the same continuity constraint up top. That's not going to change. What I've changed is this value right here. So this 2.318, 3.526, and 4.157. Those are our new assumed flow rates through pipes A, B, and C. There's really nothing else we need to do besides save it before running it. So let's do that. I'm going to go right click and run as. So that's solved another 12 times. I'll click on View and Refresh Catalog, and then select these 4 paths, and then open up the table. And let's go ahead and record what we have for iteration 2. 1.74, 3.84 for pipe B, and then 4.42 for pipe C. Now you can see that in the first iteration, we were off 2.6, almost 1, and then a 1.7. approximately. Now we're a lot closer. You can see that our assumed flow rate and the calculated flow rate are off by about zero point 0.5, zero point 0.3, and zero point 0.3. So as these numbers converge and become the same number, then we've solved the problem. So that's what we're going for. And what I propose we do for iteration 3 is the same way we started iteration 2. I'm going to just copy that equation, which is going to give us a first guess an assumed flow rate of types A, B, and C of basically the average between the numbers that we got from the previous iteration, which is 2.029, 3.683, and then 4.289. Okay, so I'm going to minimize Excel, close that. I need to go back to my constraints file. Okay, so that's been updated. So we have our 2.029, 3.683, and then 4.289. I don't mean to ignore this last goal, BC, but it just sort of reiterates here's B and then here's C. Goal AC is for A and C, and then AB is for A and B. Okay, so make sure I save that. And let's go to our RIMS, right click, and then run. So that ran and refresh. All right, here are the numbers. Drum roll, please. 1.998, 3.695, 4.307. 4.307. Okay, we're getting pretty close here. Look, we're 0.03 off there. We're about 0.012 off there and about 0.03 off there as well. So looks like we pretty much got it solved, but just for being complete, let's run it one more time with these numbers right here. Again, I'm just splitting the difference, but it looks like we've found our solution. All right, here is the constraint file and paste. So here are our new numbers that we're assuming for the flow rate, which is a pretty safe assumption at this point. Let's go right click and run it in RIMS. And back to our decision variables. So view, refresh, and then select those fields there. Okay, now we're on 2.013 and then 3.689 and it's covered up 4.298. Okay, well, we're perfect for pipes B and C and we're off 1,000th CFS for pipe A, but that could just be a rounding error or maybe I need to extend the significant figures. But regardless, we got it done, we got it solved, and it took 4 iterations. It may be silly to use this methodology for solving a problem, but I really disagree. I think some nonlinear programs can be solved very efficiently and quickly using linear programming with successive approximations like what we did in this lesson here. Now, it took a long time to actually type in new numbers and keep track of it here, and I understand that, but I think that's actually helpful for me to understand it and also to explain it in a video format. But I could probably just use RIMS, multiple sequences and models, and then run the iteration multiple times until convergence has hit. I don't know if RIMS has that logic built into it, but there may be a way to do that. But anyway, that is it for this exercise. What we did was create a network model and set it up where we had a nonlinear program that was solved using linear programming and successive approximations.